This assessment asks us to justify the position of the equilibrium for each step in the Dieckmann reaction. Some of these steps can be justified based on pKa's, acid-base reactions. Some of them can be justified based on delta G. So I've gone ahead and written in the pKa values for the appropriate molecules in this mechanism. In this first step, the equilibrium favors the reagents because the reagents are a weaker acid, they're more stable, they're less reactive, and therefore the equilibrium favors the reagents in step number 1. In step number 2, we can talk about delta G. This is a reaction that goes from one molecule to one molecule, so delta S is approximately 0, and delta H is negative, and so delta G will also be negative, and so this second step, the intramolecular step, is favored toward the products. The third step, we can also talk about delta G. We are breaking a carbon-oxygen single bond and forming a carbon-oxygen double bond. Delta H is negative. We're also going from one molecule to two. Delta S is positive. The both of those combine to make delta G negative, and therefore this step also favors the products. In the next step, we're doing another acid-base reaction. The proton between the two carbonyls has a pK of about 11. We're deprotonating with ethoxide, and ethanol has a pK of about 16. So again, the weaker acid will be the favored side. Ethanol is weaker, more stable, less reactive, and so the fourth step will also favor the products. And the final step is also an acid-base step. The hydronium ion has a pK of approximately -2 or so, and we're forming another hydrogen between the two carbonyls, another beta dicarbonyl hydrogen with a pK of about 11. Weaker acid wins. It's the more stable. It's the less reactive side, and so this last step also favors the products.